Okay, so in this video, we'll use Python to solve the multiple reactions in a CSTR problem that we introduced in the last video. So in this, to solve the multiple reactions in a CSTR, we're going to do, it's a little bit different of our solution procedure than we're used to using with Pythons. We're used to using Pythons to solve systems of ordinary differential equations for solving problems involving tubular reactors. The solution to the CSTR with multiple reactions is actually a system of algebraic equations. So it's a little bit different there. As usual, I'm going to initialize the different packages I need by pushing Shift-Enter here. Now in this problem, we've set up here the general variables, so the initial concentrations that are being fed to the CSTR. We said that A was fed at a concentration of 3 molar, but nothing else is fed. We're given a volumetric flow rate, that's given here, and then since we want to write our mole balances in terms of flow rates rather than concentrations, we use the inlet concentrations and the inlet volumetric flow rate to convert. We're given the rate constants for the different reactions, and usually we're going to be given a volume. In this case, we're asked to solve for the volume. So in reality, we don't need Python to solve this problem as long as we've gone through and calculated the inlet flow rates and then done the same for the outlet flow rates. We have rate expressions, which we have values for because we were given the operating concentrations. We could manipulate any one of those mole balances and solve for the volume. And in fact, we should be able to solve for the volume in each mole balance and get the same thing. But I would like to demonstrate how to use Python to solve systems of algebraic equations so that we can demonstrate how to solve CSTR problems involving multiple reactions. So I'm going to use Python here to solve for the volume. So to do that, I'm going to start with a guess of a volume, and I'll get to y in just a second. This is my model here, so I've called it CSTR. Basically, it's going to return the different concentrations that are exiting the CSTR. What we're doing here is converting those into flow rates in the same way that we did the initial flow rates up here. These are all of the rate expressions that were given to us in the problem statement, and then we use those to construct the net rate expressions, which we did in the last video. And so now here is some different syntax. Basically, I'm going to write the mole balances for my different species, A, B, C, D, and E. But I'm going to set those equal to 0. So what I want to do when I'm going to use this code down here, fsolve. What that's going to do is it's going to set all of these equal to 0. So I want to make these functions equal to 0. So I want to rearrange the mole balances so that they're equal to 0. One thing I have to do is provide a guess at what the concentrations should be. So this is going to solve this Python code is going to solve for these concentrations, so these things that I define here. And so I have to give a guess as what those should be. In this problem, I actually know that answer because I was given that information. So I'm going to put that information here. So this is a guess at the outlet concentration of A, B, C, D, and E. Now, in this problem, it's a little bit different because I've given that information and I'm asked to solve for the volume. A more typical problem that you would be given would be that you'd be given a volume and you'd be asked to solve for the concentrations in the CSTR, in which case you would have to enter a guess here. So enter a reasonable guess of what you think those values should be. And sometimes you're going to make good guesses that are going to lead to a solution, and sometimes you're going to make bad guesses that don't lead to a solution. If it's one of those cases where you make a bad guess and you don't get a solution, just spend a little bit more time thinking about what would be reasonable guesses for the different concentrations in the reactor. For example, if you have a species that's a reactant and it's not being generated in any reactions, then you want your guess at your outlet concentration to be lower than your inlet, for example. You can also kind of look at the relative rates of things. If B is being generated at 4 times the rate of C, then you probably want to have your guess for B in this vector be a little bit larger than your guess for C. A lot of times, as long as you get kind of anywhere in the ballpark, Python will solve it. Sometimes, we don't always make the best guesses. So in those cases, just think about what the problem is doing and what you expect the answers to be and adjust until you get something to solve. So now, once I have my guess at what the outlet concentrations are, I can just say I can use fsolve to solve it. I'm going to solve the model pursuant to my initial guess. In this case, like I said, I know what my outlet concentration should be. So I want to enter in a volume that's going to land on exactly these outlet concentrations. So to do that, I want the difference between the solution and my guess to be 0. So that's what I'm printing here. That's this first thing that's going to be printed. And the second line that's going to be printed is basically saying, okay, now tell me what this model is equal to. So tell me F1, 2, 3, and 4, and I want that to be equal to 0. That tells me that fsolve worked. And if I look at these values, they are all pretty close to 0 or identically 0. So let's solve this. And the first line that I get is this one. So the difference between my solution and my guesses for what the solution should be. And again, if I got the volume right, those should be 0. As we see, I didn't get 0. So let's play with the volume. If I change it to 100, I get a different solution, still not 0. 200, still not 0. 300. Getting there, so everything's kind of looking closer to 0, but I still don't have 0. 400, okay, so now I'm at 0. So now if I look at the difference between the solution of my concentrations and my guess at what they should be, I get 0. That tells me that the volume is correct. Operating concentrations as are defined here. So you can modify this template for other CSTR design problems involving multiple reactions.